Well, in this segment, we'll look at some famous experiments that were done by Andre Ampere in the early 1800s. Ampere is kind of an interesting guy in that he was totally self taught and ultimately arose and came up and was obviously a genius of high order. And even though he had no formal training, no formal PhD, no university education at all, he was taken into the faculty at one of the premier universities in Paris. And and so yeah, I guess probably would be unheard of now, no matter what would happen. But people when they recognized the talented people, they seem to have gotten rewarded for it, even in all the turmoil that was going on in France at that time. Uh, but let's get into Ampere's experiments. What he did, 1823. Remember, is only a couple of years after Ørsted had announced his discovery of the that currents produced magnetic fields of electromagnetism, and Ampere began to investigate the magnetic force and the magnetic fields produced by current carrying wires. And in particular, he had a very unique arrangement in which he had two very, very long wires, actually rods, metal rods, that were long and straight. He connected currents up to them. Again, this is in the early days, no mean feat to be able to produce currents even. And essentially had a current loop in which he ran current I1 down this one, and then or he could produce a current I2. Now, usually he made this into a loop, and so I1 and I2 were the same, and so they were going just in opposite directions. And he could measure the distance between these two parallel rods, metal rods, and he could develop the current in it. And like I say, usually he didn't really know what the current was. He just knew that there was charges moving through these, and they would so he would just send essentially an unknown current down this rod, and then a similar unknown current, the same current coming back. And by this time, he knew Ørsted's results. And so long as the wire is very, very long, like an infinite wire, then for this wire, if I look at this from this end, looking inward, then I1 is going away from me if I look at it from this side, and I2 is coming toward me. And I'll keep those as I1 and I2 just so that I can distinguish them. But again, usually they're the same value for the current. And for I1, we know that it produces a magnetic field, B1, everywhere about it. Ørsted, mu naught over 2 pi, I1 over the distance r you are away from. And so it swirls about using that right hand rule. Grab the rod in the with your thumb, with your right hand, thumb pointing in the direction of current flow, and your fingers naturally curl in the direction of these circulating magnetic fields about it. So the current I1 produces everywhere about it a magnetic field. But Ampere also knew the magnetic force, that there were forces on current carrying wires, and that had this expression. And so this magnetic field produced by I1 creates the current I1 produces this magnetic field here at this point. That's the magnetic field produced by this current. And then I2, as a result of that, experiences a force, which is I L vector cross B. In this case, the B is produced by 1. So if you plug in the numbers, the distance from the first rod to the second is D. I'm assuming they both have the same length, L. So the strength of this magnetic field B1 is mu naught I over 2 pi d by the Oersted long infinite wire relation. And so we know B, we know its direction using our right-hand rule. And then I can compute the force on rod 2 over here. Now that's the force on 2 due to 1. So on 2 due to 1, I've got it right over here. This is your book's notation. I wanted to point that out. So sometimes you see 1, 2, and I think your book writes it like this. But I like to put the first one as what the force is on, and the second one what's causing the force. So this is the force, the way I look at it, on rod 2 produced by book 1, or by field, the magnetic field 1, which was produced by I1. So force on 2 due to 1. Now your book likes to write the force caused by 1 on 2. So whenever I read something, I don't pay close attention to those. I just figure it out myself, and then I understand what the author's notation. So probably equal numbers of people use these two different notations. So don't get confused by the book, and that's the reason I threw that in there. But in my notation over here, the force on 2 due to 1, well, I use this formula above. It's the current I2. This is the force on 2, and I would ordinarily use length 2, right? And the magnetic field that's over here was the magnetic field produced by current 1, so it's B1. And if you look at those, they're at right angles. The current's L vectors coming out at me, and B is going down. So if you use your right hand rule of 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 L vector cross B vector. Yeah. Now I was just trying to figure it out. It's DL vector is coming out at me, B going down, and so yeah, the right hand rule gives the force in this direction. So I just somehow or other I was thinking of it backwards. But they're at right angles. The DL is coming out of the page, B is downward. So L2 is out of the page, B is in the plane of the page, and so the angle is 90 degrees. And so the magnitude of F21 is just I2, current going through this, times L, its total length, and times B1, the field produced at this point. And if you plug this result for the magnitude of B1, you get this case here. So I just plugged mu I 2 pi d in for B1, and then the I2 and the L are here. And as you see, it's repulsive in the sense that it's pushing the second rod away from the first rod. Now I could do the same kind of analysis and treat this, get the magnetic field produced by I2 over at I1 and see what force it produces. But I don't really have to, because I can use for every Newton's third law, for every action there's an equal and opposite reaction. And so the force on 2 due to 1 has got to be equal and opposite to the force on 1 due to 2. And so in this case of two currents going in opposite direction, you get a mutual repulsion of equal magnitude, both of them be of this form here. Okay? And that is mostly the way that Ampere ran his experiments, with the exception that he usually had the same current going through them. That's the easiest one to produce. It's just same currents just going in opposite directions. If we had the other alternative, if I have two currents going in the same direction, same analysis really. The magnetic field B1 is still going downward, but now the only thing that's changed is I2 instead of coming out of the page is into the page. And if you use the right hand rule, the magnitude's exactly the same for the force. It's just direction has changed. And so in this case, the two mutually attract. So currents going in the same direction attract each other, and currents going in opposite direction repel each other. Well, nowadays it turns out it's very, very easy to measure currents, yeah? And one can generally measure currents to much higher precision than you can measure charge, for instance. And so, because of that precision, what people do, or what people did, was they can measure forces to a higher degree of precision. Of course, lengths, the length of the rod, the distance of separation, those you can measure to high precision. And since you can measure currents to higher precision, what they do is they use this relationship between these parallel rods to either force of attraction or force of repulsion to measure the force, uh, measure the distances, measure the currents, and then let this constant here be determined by this force law in the following sense. Yeah? And this is the way we do it nowadays, is that we define 1 ampere as the current that causes a magnetic force per unit length of precisely 2 times 10 to the minus 7th Newton per meter. And why force per unit length? Well, if I divide this F by the length, I get a force per length here. It produces that force when you have exactly uh, a equal currents flowing in generally opposite directions to get repulsion. So they have the same current flowing, and one simply adjusts the amount of current here, amount of current, until the force per unit length for a given L and D, that they adjust the amount of current, both the same, and you do that until you get a force per unit length. When this distance of separation D here is 1 meter, so they have to be fairly long rods. That repulsive is 1 meter away, so they have one meter separation. That's our little d, and the force per unit length is this. When I'm running exactly the same current through both of the wires, and I adjust the current until the force is this force per unit length is here. Okay? And what that does is I then have a definition of 1 ampere. So I'll have 1 ampere squared. I know this is 1 meter. I've measured the length, and I measure the force, so I get the force per unit length, and that fixes this constant, this fundamental constant, mu naught 2 pi. So we fix that. Again, I becomes 1 ampere, D 1 meter, and you adjust the currents until you get this force per unit length. And then everything there is known except for this. The 4 pi is by convention. But in any event, when you do that with 1 ampere flowing in both of these in opposite directions, you find that the value for mu naught for the vacuum is 4 pi times 10 to the minus 7th Tesla meters per amp. So this is what I had given you earlier. Remember, a Tesla, I always forget what a Tesla is, but I can use this relationship for a long wire. B is always in Tesla. Mu naught, I is in amperes, R is in meters, and so mu naught should have the units of Tesla meters per amp if I rearrange this. And that's what I've listed in here. And that's the one that I find most useful. But very, very often when I look this up, what I get is this value, 4 pi times 10 to the minus 7 H per meter. And H here is for henries. And we'll get to henries maybe a little later. But by definition, a henry is a Tesla meter squared per amp, and it's abbreviated H. Uh, well, once you've defined an ampere of current and can measure that in this fashion, then uh, you then define the coulomb to be the amount of charge that flows past a given point when the current running through the wire is 1 ampere. So I know what the unit of ampere is now. I've got a unit for it and a scale for it. Current, of course, is just delta I or delta Q over delta T. And so if I run 1 ampere, the amount of charge that flows past in 1 second, it's actually a lot of charge, uh, is, uh, is defined to be 1 coulomb. So we don't really introduce coulombs based on Coulomb's law, but we introduce coulombs based on Ampere's law and this current and charge and time relationship. Well, that's the basis of our units, at least in modern day physics. There's other sets of units that don't do this procedure, but certainly the SI rationalized MKS units use this procedure of defining the ampere as really the fundamental, and then charge, the Coulomb unit, is derived from that.